Hey guys, today we're going to do the second video in our nuclear chemistry chapter. So in this section, I'm going to go over how to do half-life reactions with you, or half-life equations. So this idea of radioactivity, this idea of unstable isotopes emitting some sort of radioactive particle, this is just a natural component of the environment. So of all of the elements on the periodic table, from element 83 and any of them that are bigger than 83, so in the position down on the periodic table, these are all going to undergo radioactive decay naturally. And many of these really, really big ones down here at the very bottom of the periodic table, they radioactively decay very, very rapidly, like within seconds or milliseconds. So radioactive decay is just a part of nature. It happens without us having to do anything. When we look at how radioactive decay happens, we can look at the rate of decay. And for the rate of decay, we talk about something called a half-life. So a half-life is the time it takes for half of the parent nucleotide to decay, or half of the original sample to decay. So here we see an example of iodine here in purple. So after one half-life, half of the iodine becomes something else. Half of the iodine is still there. That's a half-life. After another half-life, it's not that two halves equal a whole. So it's not that after two half-lives, all of the iodine's gone. What instead happens is after another half-life has gone by, half of what was left now dissipates. So let's say we had 10 grams here. After one half-life, we had 5 grams. And now, after another half-life, we would have 2.5. So each half-life, whatever is left, half of that disappears. So it's not 2 halves make a whole. It just gets divided by 2 after each half-life. Half-lives vary vastly between element to element or isotope to isotope. So here we see thorium-232. It has a half-life of 14 billion years. So if I have 1 million atoms of this thorium, after 14 billion years, I'm going to have 500,000. So what this tells me is thorium breaks down very, very slowly. So it must be pretty stable if it takes that long to break down. So this is a pretty slow half-life. I'm trying to click forward here. Something like radon-222. This has a half-life of about a minute. Okay, so a much faster half-life. So if I have 1 million particles or atoms of this, after 1 minute, I'm going to have 500,000. So this is something that we could probably watch it decay right in front of our eyes. That's a pretty fast half-life. So we can watch this for a minute and we'll see that half of those particles will change into something else. So as I said before, the rate of decay for different isotopes is very, very different. It's all over the place as far as the rate of decay. So here's an example of a problem that you would be asked to do. So how long does it take for 1.8 mole sample of thorium-228 to decay to 0.225 moles? And it also gives you the half-life. So the half-life is 1.9 years. The best way that I found to solve these problems is to make a table. It's a little bit tedious to have to draw a table for every single problem, but it's the best way to organize the information and work through it in a organized fashion. One of the biggest mistakes I see is setting up the table. So once the table's set up, you guys can navigate through it pretty easily. When you set up your table, you need to make sure that you set it up at time 0. So we started with 1.8 moles. So that's going to be the first number that I put down. So the amount is 1.8 moles. And then in that line, that's after 0 half-lives and 0 time has gone by. So the biggest mistake I see is people start with number 1 here. So like, oh, after 1 half-life, and that's incorrect. So this is how much we had at time 0 before any time has elapsed. Okay. So then we're just going to start working through this problem until we get to the 0.225 moles. So we're going to let 1 half-life go by. That's going to be 1.9 years. And the definition of a half-life is that this 1.8 moles is going to be cut in half. So 1.8 divided by 2, we get 0.90 moles. Okay. And we just continue this process until we hit our goal. So another half-life is going to go by. So 1.9 plus another 1.9 years is 3.8 years. And after 3.8 years, this is going to be cut in half. So 0.45 moles. And we continue. So after 3 half-lives, that's going to be 5.7 years. We're going to cut the 0.45 in half. And that's where we get to the destination, the 0.225 moles. So it's asking, how long does it take for this to go from 1.8 moles to 0.225 moles? The answer is over here. It's going to be 5.7 years. Pretty straightforward, pretty easy arithmetic here. So here's another example. We have phosphorus 32 is used in the treatment of leukemia. It has a half-life of 14.3 days. If a sample of 8 milligrams of phosphorus was given to the patient, how many milligrams of phosphorus would remain in their system after 42.9 days? So go ahead and pause the video and see if you can work through this on your own. All right, so the first thing I'm going to do is I'm going to set up a table. So the table that I set up is going to be the amount of the isotope. Then I'm going to put the number of half-lives. And then I'm going to put time in. And I'm just going to click back real quick and see what this time is in. Okay, so they gave us a half-life in days. So that's going to be time in days. Okay. Remember, we always start our table at time 0. So after 0 half-lives and 0 time has gone by, how much did the patient take? Well, the patient took 8 milligrams. So that's going to go here. All right, so now our table's set up. Now we just need to start going through this. So it wants us to go through this table till we get to 42.9 days. So I'm just going to work through the table till I hit 42.9 days. So after 1 half-life, that would be 14.3 days. We would have this isotope break down to 4 milligrams. Okay. And then after 2 half-lives, so after 2 half-lives, that would be 28.6 days. This isotope would break down in half to 2 milligrams. After, whoa, that's not what I wanted. Wait, I'll close it. All right. So after 3 half-lives, that would be 42.9 days. Okay, so that's the goal we were trying to get to. And this would again break down in half, so it would break to 1 milligram. So it's asking us, the patient took 8 milligrams on day 1. After 42 days, how much will be left in their system? Well, the answer is 1 milligram. So it'd be 1 milligram of the isotope left. So that ends our discussion on half-lives. Those are the only 2 videos that I'm going to do out of chapter 5. I think the rest of it is pretty straightforward information that you can read your textbook. I hope you enjoy these videos.